Spencer, you can move that like 3 inches.
Taking the test.
The camera or me? Why? Oh, it's hard to read what's on the board. Well, if I move any closer, then
Not for me.
he's talking about the video.
Yeah, it was pretty hard.
Okay. I am going to do my absolute best to. I'm yelling at this poor screen. These people are going to be like, "Why is he yelling?" Awesome. Yeah, no, I know. I actually could probably just write bigger, but it's the same problem either way. Okay. Matt missed class, and so he had to watch was it the last lecture? Yeah, so he feels the pain. Anyway, all right, so we're going to get started with a very brief review of where we left off last time. And by the way, I do not in any way, shape, or form think this is the most enjoyable part of this course. In fact, this is it's the sort of technical punishment that you must go through, trial by fire kind of thing, and then after this, it's going to get very nice and elegant. So trust me, if you can just stick it out through the rest of Spinors, the next part will be very inspiring. But we have to get through Spinors. So where we left off last time, in case you don't recall, working with objects that are sort of intuitively defined based on coordinate type quantities, both position vectors and various tensors like velocities and momentum and so forth. We found that the special relativistic set of transformations takes the form SO1, 3. And then we took the generators of that, the 3 rotation generators J, the 3 boost generators K, and we discovered that if we formed linear combinations J plus and J minus of those, then this algebra of SO1, 3 actually split up into 2 separate SO3 algebras. This is a little weird because it's not like this is the rotations and this is the boosts. That's not the way it works. This is a combination of rotations and boosts, and this is a combination of rotations and boosts. So it's really hard to point to this and say what this is or what this is. So don't try it. There's nothing intuitive about it. Yes?
Can you remind me, what does it mean for something to be an algebra or to split into an algebra? Or why?
So when we looked at this algebra, what we found was that the rotation generators formed the usual rotation algebra. But if we took 2 boost generators, then, and I might get the sign wrong, then these actually did not form an algebra, a closed algebra, because if you took 2 boost generators and you formed their commutator, you actually got back a rotation. So, and then you can also ask what happens if you do a J and a K. And if you do a J and a K, it turns out this is generically non-zero. So what we did was we formed linear combinations, J plus and J minus. They're just linear combinations of these. But the benefit to these linear combinations is that if I do J plus I, J plus J, I get exactly the algebra of rotations, even though these aren't technically rotations. That's the same algebra as this one. But then if I do the same with J minus, I get the same algebra. That is, if I do minus, minus, I get back minus, and then if I mix them, I get 0. So these 3 statements, the plus version of this, the minus version of this, and the fact that they don't talk to each other is why we can say we have an SO3 and another copy of SO3, and the cross just kind of means they don't talk to each other. Okay? That was not happening here. We had to take the linear combinations to get it to happen.
And you need both the plus and the minuses to describe the entire set.
Yes. Yeah, if you just tried to work with J plus, right? J plus I is, I think, J I, was it J I plus I K I? Was there an I in there? Does anybody remember? Yeah. Plus I K I. And if you just use J plus, you'd be missing half of the generators. Because you'd only get 3 of these, but there's 6 of these. So you need to have 6 things here if you're going to try and describe the entire set of transformations. Any other questions on that? This was kind of the last point we made, and I stayed after quite a while and talked to some people about what this means. So
In your notation there, do you have to choose plus all the way across or minus all the way across?
Yes, yeah. So if you do a plus and a plus, you get a plus. That's the nice thing. Because the problem here is I do k, k, but I get back a j, and that's what screws this up, in addition to this one. Okay? By the way, if you look at this algebra, the j's actually could form a subgroup. Because if you take two j's, they give you back a j. But the k's could not form a subgroup. Because if you took just the k's, if you combine two of them, you'd get back a j, which is outside of that set. So you could not form a subgroup of boosts, even though you could form a subgroup of rotations, which you might have expected because we had already talked about the group of rotations before we ever talked about relativity. So we knew that had to form a group. It's just that the boosts by themselves don't form a second group. Okay? All right, so the advantage to beating the algebra into this form is that we are now in a position to take advantage of all of the stuff we did to introduce spinors in the non-relativistic case. Because in the non-relativistic case, we just observed that SO3 has the same algebra as SU2. And so instead of 3 by 3 real matrices acting on 3-component vectors, I could imagine 2 by 2 complex matrices acting on 2-component spinors. But I have a 2-component from here and a 2-component from there, so altogether it's a 4-component spinor I call psi. Okay? And the properties of these 4-component spinors are what we're going to talk about in detail today. So the first thing we have to ask is, so how does a psi transform under a Lorentz transformation? We know that the details are kind of hiding in these algebras because these are derived from the transformations, although we did this funny step here of, doing linear combinations, so the precise answer is maybe a little obscure. But we would like to figure out how these things transform, and then from that, how we would go about forming an invariant. And in the course of discussing this, we're going to come upon some things which I think many of you have probably heard of, but you might not know completely what the origin of those things are, and we'll talk about that in just a moment. So there are a couple of ways to talk about how psi transforms, but I think the sort of deepest way to get at it is carrying through with this thing I talked about, I don't know if it was last time or the time before, but this idea that spinors represent somehow the square root of the geometry. Okay? So if we remind ourselves an expression that I wrote for rotations or spinors for three-dimensional rotations, we said that if I take the anti-commutator of two Pauli spin matrices, then that just gives me 2 times delta ij times the identity matrix in spin space. And we identified, so remember ij goes from 1 to 3. So we're just talking about purely spatial rotations, x, y, z, or 1, 2, 3. And so this guy is really the metric of the space that those rotations happened in, because in 3 flat spatial dimensions, in rectangular coordinates, the metric is just the identity. So what we could do is we could say, okay, in 4D space-time, maybe what I could do is just write down the closest analogy to this that I possibly can. Okay? So what I would need is a set of things which have an index which goes from 0, 1, 2, 3, and we usually use mu's and nus for that, so I'm going to give this an index mu. And then I could take the anti-commutator with another one with a different value of the index. We'll understand in a minute why I'm putting these up instead of down. Bear in mind, for this thing that I wrote here, you could have put all of the indices up and it wouldn't have changed anything. Okay, because in this space, up and down doesn't mean anything. Here, I'm just going to go ahead and put these up, and we'll talk in a minute about whether that was the right thing to do. And then what we can say is that this is, we'll just put the number 2 in there. Why would we mess with 2? 2 is a great number. I like 2. But now we want to replace this metric the identity in 3 spatial dimensions with the metric of flat space-time, which we know is, well, I'm going to write the inverse metric just to get the indices to match up, which is eta mu nu, okay? Now remember, these things are 2 by 2 matrices. So when I write this thing sigma, you know, sigma x I hat plus sigma y j hat plus sigma z k hat, I must remember that these are secretly 2 by 2 matrices. So I think of sigma as a vector of matrices. It's a vector in space because it has x, y, and z components, but it's a matrix in spin space. Okay? Where spin space is this little 2-dimensional complex vector space. And that's where these 2-dimensional matrices act. So at this point, what kind of objects do we think these gamma mu's are going to be? Say it again?
Vector of 3 by 3s?
Well, what are they going to act on? So what do these act on? 2-component spinners. So what do you think these are going to act on?
4-component sign.
4-component spinners.
Yeah.
So these are going to be 4 by 4 matrices in spin space. Okay? But this is just a metric of space-time. This has nothing to do with spin space. It is a 4 by 4 matrix if you write its components, but the 4 by 4 of this has got to do with the mu and the nu here. It doesn't have to do with the fact that this itself is a 4 by 4 matrix. Okay? So with that in mind, what do I need to add to this expression for it to make sense?
4 by 4 identity.
Well, not add, but say it again?
4 by 4 identity in spin space.
Yeah, so I need the 4 by 4 identity in spin space. So this is a, if you will, a matrix in space-time, and this is a matrix in spin space. They both happen to be 4 by 4, but that is it's a very inconvenient degeneracy because the 4 here and the 4 here have really not very much to do with each other. Okay, it's less confusing here because it's a 2 by 2 matrix, but this is 3 by 3. Okay. All right. So carrying through this analogy, in the spinor case for rotations in flat space, we say that if I have a spinor chi and I want to transform it, then again I use the exponential map. And writing the generators in terms of the Pauli matrices, I have that I exponentiate I/2 times sigma dot theta, where theta is the vector of parameters. So remember, theta I can think of as a set of theta, phi, and psi, an angle for each axis I want to rotate around. And so you can imagine that the generalization here would be that psi goes to psi prime, e to the I/2, and how am I going to, yeah, gamma dot theta psi, something like that. And then in this case, theta would be something like, I don't know, omega, theta, phi, psi. Okay, I would need 4 things here. I mean, really and truthfully, I should write this like this, just to be honest. I should write this as gamma mu theta mu. And since there's four values for mu, there would be 4 values for this mu, and I'm just giving them names. Okay? So I am trying to play on the analogy with what we did for spinners and 3-dimensional spatial rotations. But this doesn't work. Why does it not work? How many independent transformations can I do in this case? Here, I'm going to start drawing cards. Caleb, how many independent transformations can I do in the first case? 3, right. Rotations around X, rotations around Y, rotations around Z. Patrick, how many independent transformations can I do in this case? 6. Yeah, I can do 3 boosts and 3 rotations. But the problem is that this is only describing 4 things. It works here because there's 3 angles and 3 axes I can rotate around. But somehow I want to be able to do 6 different transformations, but I've only got 4 things to work with. Brad. Man, it's like clusters in the side of the room. Brad uses memes, as he announced on his ID card. Brad, if you were making a meme of this problem, what would be the solution meme to this problem?
A symbol for every plane of rotation.
Say it again?
A symbol for every plane of rotation.
Yes, that is exactly the right solution. The problem is really that we're using terrible notation. Okay? Really and truthfully, I shouldn't call this a rotation around X, but rather a rotation in the YZ plane, a rotation in the ZX plane, and then I should call this, well, I don't know what to call it. I've never written the metric with these kinds of indices. But the problem is that we're trying to label things by axes, and that works in 3 dimensions, because remember, in 3 dimensions, if you specify a plane, there's a unique normal. So you can interchange plane with normal. But in 4 dimensions, that breaks down. Because if you pick a 2-dimensional plane, there's 2 normals to it. So which one are you talking about? So in order to get around this, what we're going to do is we're going to write this slightly differently. So instead of thinking of sigma 1, sigma 2, and sigma 3 as the sort of generators of rotations in 3 dimensions, we can recall the algebra. And what that does is it says, well, if I want to write down, say, sigma z, then I can express that as sigma x, sigma y. And then moving the I to the other side picks up a minus sign. And so now sigma x I can realize is minus the commutator of sigma z, sigma y. Sigma y would be minus the commutator of sigma z. Oh, sorry, no, this was yz. Sigma z, sigma x, and minus the commutator of sigma x, sigma y. Okay, so what I'm saying is, instead of thinking of that thing as the generator of a rotation around the x-axis, I should think of this as the generator of rotation in the yz plane. But these things are equivalent by the algebra. Okay? Is that what you meant? The correct answer is exactly. Okay? Does everybody understand that in this rewriting I haven't changed anything? Because if you literally took the matrices and you formed the commutator with a minus sign, sorry, there should be i's in here, I'm leaving out the i's. Every one of these should have an I in it. But if you form the commutator multiplied by minus I, you would get exactly sigma x. I'm just giving it a different name. But what's nice is it solves our conundrum. Because what we can do now is we can say that instead of trying to think of gamma mu, gamma, or 4 gamma mu's, what we'll do is we'll say, I'm going to consider minus I over 4 gamma 0, gamma 1 as one generator, et cetera, et cetera. And this should be 2, 3, 3, 1, and gamma 1, gamma 2, just to get the ordering right. Okay?
Alex,
Yeah.
quickly again, could you say where you're getting the negatives from?
So, yeah, if I multiply both sides by I, I get an I here, I get a -1 there, and then I move the minus over.
Gotcha.
Yeah.
So this is essentially equivalent to saying rather than parameterize our theta by individual like omega, theta, psi, phi, whatever.
Well, what we are gonna do that because what we're gonna now say is that when I do a transformation, I've got to give you a parameter for this, a parameter for this, a parameter for this, a parameter for this, this, and this. These are just rotations. I mean, this is the YZ plane, so I can think of it as just a rotation. But these are boosts, so maybe we'll do alpha, beta, gamma as the parameters for those. But we're still going to have a set of parameters. But what's important is we're going to have 6 of them, because we have 6 different combinations, which is what we expect.
If you think about expanding the algebra though, you'll have 2 terms on the right-hand side. You'll have a sum of like one of the components and another one of the components. So if you think about the possible summations of 4 parameters, you get 6 possibilities out.
Wait, say it again?
So if we start with 4 parameters, as we did before but it was wrong, and then we try and make sums of 2 of each of them as the algebra on the right-hand side, which you arrive at, you get 6 possible 2 combinations of such.
Well, you've got to be careful because if you take 4 things and then you form a bunch of linear combinations, at the end of the day, there's only 4 independent things you can vary. Because varying those things determines all the linear combinations. I'm saying there's 6 completely independent parameters that I can vary. So I don't want to try and associate them with the parameters, this set of 4 that I started with on my sort of ill attempt. Rochelle?
Like, we might have gone over this in the video or something, but like, when we have 4 different inputs, how do we know, like, whether we go like 0 to 2 or like 2 to 0?
So at this point, okay, at this point, it's not, at this point, I'm literally just making a list of things and the order is not that important. The reason I'm being so careful about order for these last 3 is because we like to order rotations in terms of rotation around X, rotation around Y, rotation around Z. Here I'm just boosting in X, boosting in Y, boosting in Z. So I'm writing the corresponding combinations that correspond to that ordering, but there's nothing sacred about that ordering. Ariel, do you have a question?
Yeah, where did the gammas come from? Because we had J and K notation before for the generators now.
Okay, so I haven't told you what these are.
Oh, okay.
What I've said is, if I write down something analogous to this, it looks like this, okay? And if I try to play with these gammas in the same way that I used the sigmas before, it almost works, except there's this problem, we only have 4 things. So what I did was I went back to the sigma story and I said, let's actually think about the sigma story slightly differently. And instead of thinking about sigma 1, sigma 2, sigma 3, let's actually talk about commutator, commutator, commutator. And now if I play that exactly with this expression, I get something that seems to be working. I still have a lot of details to flesh out. Okay? So the moral of all this is just going back and reiterating a point I made long ago, which is when you talk about transformations, you should be careful not to talk about transformations around an axis, but you should be talking about planes. Because that works in 3, but it doesn't work in 4. Okay? And now we're going to beat on this story a little bit more.
And we assume that gamma follows the same algebra as just the sigmas, just by assumption.
Yeah, it's just an assumption. So if these squared to give you the metric, let's just suppose that these square to give you the metric. Okay. All right. So what is this actually going to look like in detail? Well, to give the parameters names, instead of calling them theta, phi, and psi, it's better to index them with numbers because then you can use summation. You know, it's the sum over theta, phi, psi, alpha, beta, gamma. I don't even really know how to do that. So if we want to indicate how one of these things transforms, we're going to use the following rules. Psi goes to psi prime which is going to be e to the I over 4, sigma mu nu omega mu nu psi, where each of these things is a sigma mu nu. So this would be sigma 0, 1, this would be sigma 0, 2, etc., etc. Okay? So we're just more conveniently, more accurately labeling our generators by a 2-index thing instead of a 1. That way you can easily see, oh, that's the plane I'm doing it in. Okay? Now from this, we can immediately see that sigma 0, 1 is minus sigma 1, 0. Because if I just reorder the things inside of a commutator, I always get minus. Okay? And then it's the omegas that are going to take the place of those things alpha, beta, gamma. So alpha, beta, gamma, theta, phi, psi is going to become the set of parameters omega 0, 1, omega 0, 2, omega 0, 3, omega 2, 3, omega 3, 1, and omega 1, 2. Okay, so a boost along x, a boost along y, a boost along z, rotation in x, rotation y, rotation z. I'm now going to instead call them those things. And then this summation says, just to be really concrete about it, by the way, these parameters are also antisymmetric. So this is minus omega 1, 0, et cetera, et cetera, et cetera. So just to show you concretely how this works out, if I wanted to do a rotation in the YZ plane by an angle phi, so I want to use, I don't want to use that guy, do a rotation by theta in the YZ plane. Then my omega mu, or my omega mu nu set would be 0, 0, 0, theta, 0, 0. Okay, because I'm only using the rotation in the 2, 3 plane. I'm not doing anything anywhere else. And then when I form the actual transformation, I have psi goes to psi prime, e to the I over 4, and the only term that's non-zero is omega yz or omega zy, because they're minus each other. And so here I'm going to have sigma yz omega yz plus sigma zy omega zy on psi. And by the way, that psi should not be in the exponent. But this is related to this by a minus sign, and this is related to this by a minus sign. Okay, so really this is just twice one of them. And so this is just going to become e to the I over 2 sigma yz omega yz, or theta, if you will, times psi. And now you can kind of see why I picked this 4 in these expressions. Because you're always going to pick these things up in pairs. Okay? But they're always going to be the same, so they combine to give you a 2. And now this looks a lot like the transformation that we wrote for the non-relativistic case. So the bottom line of this, if this is like, if you're lost in index gymnastics and what the hell all this stuff is I now have a rule for how these 4 component spinors transform. It is given in terms of a set of generators, which are given by these expressions, and a set of parameters given by these expressions. And to evaluate this, you just use the summation convention. And that's what I showed you in this example. I still haven't shown you what the gammas are. I'm about to. Okay? So we now have a transformation rule for these 4 component spinors that's perfectly analogous to the transformation rule that we had for 2 component spinors. And now let's flesh this out by looking at what the gammas are. Ready? Again, this is not the sexiest stuff. You should have worn a sexier shirt. But it will get cool in the next few topics, so please bear with me. So if I want to find out what the gammas are, I really just need to focus on this expression. That Clifford algebra. Because remember, when I found the sigmas, one way to find the sigmas was just to solve this thing. So if I want to find the gammas, I can just try and solve this. And if I do that, I find one set of gammas. Of course, there are different variations. But one set is 0, 1, 1, 0, where that's a 4 by 4 matrix. So this is the 2 by 2 identity, the 2 by 2 identity, and these are 2 by 2 matrices of zeros. I'm just not going to draw 4 component things, or 4 by 4 matrices. And then the gamma i's are given by minus I, 0, sigma I, 0. Or minus sigma I, sorry. Okay? Where again, I'm actually using the Pauli spin matrices, and I'll write them down correctly this time. Okay? So there you have it. You have 4 gamma matrices. They are 4 by 4 matrices. And they're kind of broken up into this sort of, it's not quite block diagonal. It's actually block off diagonal. Okay? But if you take these things, these are concrete expressions, you will find that they satisfy this expression. Okay? Now, if we just think about what we've been talking about, we can immediately recognize a few nice properties of these gamma matrices. So one nice property of the gamma matrices is that, of course, their anticommutator satisfies this expression. And then from that, if I square gamma 0, what do I get? So from this expression, and we'll pick a victim. Ariel. Ariel, based on this expression, what could you tell me about gamma 0 squared? So what are you trying to do in order to evaluate this?
I'm trying to use the right-hand side.
But how are you getting gamma 0 squared out of this expression?
Oh, I'm plugging gamma 0, gamma 0.
Yeah. So if you set mu and nu both to gamma 0, then this is the anticommutator, but the anticommutator is gamma 0 plus gamma 0, gamma 0, which is just 2 gamma 0 squared. And then that's equal to what?
2 times, and then that's negative 1, and then times the 4 by 4.
Yeah, exactly. So we would call this minus 2. Okay? It's 2 times negative 1, and then we're not going to keep writing this identity. Okay? So we could say that gamma 0 squared is minus 1. There's a 2 and a 2. Moreover, gamma I squared would be Andrew. Where's Andrew? Where's the C, Andrew? Going once, going twice. I kind of call on Steve-O.
Space Wizard Steve-O?
Yes, Space Wizard. It's so funny because when I see this picture, I'm not going to say it. You don't look anything like you. You look like something categorically different, and I'm not going to say what it is. But anyway, Space Wizard Steve-O. What do I get if I square one of the spatial gammas?
Let's see. Do you get 0?
Well, if I tried the same trick Ariel pulled and it said gamma I, anticommutator gamma I, that's going to give me 2 gamma I squared. And then what's this side?
And then that'll be...
So what is eta II? So eta, if you write it as a matrix, looks like this.
1, or -1.
Well, it's 1 if you're doing spatial. So it's one of these three.
So it'll be 1.
So this is just going to be +1. Okay?
Well,
So the gamma matrices have this nice property. They square to either -1 or +1. And moreover, these are very important, folks. You should write these down because we're going to work with these gamma matrices a lot. Moreover, if I have gamma nu plus gamma mu, and mu is not equal to nu, then what's that equal to? 0. Because if mu is not equal to nu, you're off diagonal, which means it's 0. But that implies that gamma nu is minus gamma mu when you have two different two different values of mu and nu. So this is the statement that the gamma mu's anti-commute with each other.
All right, wait, silly question. That first gamma 0,
This one?
yeah, but like when you
This
first
one.
defined it, how's that a 4x4? Okay, just big zeros? Or- Okay, sorry, yeah, cool.
No, that's the kind of question like I would have been afraid to ask, and then I do ask it, and half the people in the room are like, God, I'm so glad you asked that, because I had no idea how that was a 4x4. Yeah, that's what I mean.
Okay, cool.
Okay. Any other questions? Yeah, Spencer.
If gamma nu and not equal to nu, if those are defined by the off diagonals of the metric, aren't those always 0?
Yeah, that's what I just said.
But how is it equal to its negative then?
Oh, I literally taking this expression and moving 1 to the other side.
He has 0 plus 0 equals 0, and then he has 0 equals -0.
It's the anti-commutator that's 0, not the product of them.
I guess the whole point then, both of those statements are what? Trivial because they're both 0? Like, that's what you're saying?
These two statements?
Yeah, because each of the term, gamma nu is 0.
No, I didn't say gamma nu is 0. It's not that gamma nu is 0. The anti-commutator of gamma nu must be 0. This is the left-hand side's the anti-commutator. It's not just gamma nu. Yeah, I think that's what Brooks just said. Yeah, so you got to be careful when you're just looking at a product versus when you're looking at a commutator or an anti-commutator, because those can have very different values at the end. Okay, so again, it never hurts to be super explicit, so let's actually write down an explicit form for at least a couple of these generators. So in terms of everything that I've said, if I go back to what does a boost generator look like, so I'm going to do it for an arbitrary spatial direction I, so you could do 1, 2, 3. Then remember this is minus I over 4 commutator gamma 0 gamma I. Okay, that's all erased now, but that's what we had concluded previously. And now we can just bang this out. Minus I over 4, quantity gamma 0 gamma I minus gamma I gamma 0. And if I just crunch the numbers, and Matthew will be kind enough to let me write my 4x4 matrices as 2x2 matrices.
For sure.
Thank you, sweetie. I appreciate it. I mean that from the bottom of my heart.
Keep it.
It's like you guys are struggling with expressions of appreciation. Okay? And then if I just do all the matrix multiplication, account for all my minus signs and factors of I, and then add the two results together, I get something like this. Okay? And so now, we can see finally something nice coming out of this. The gammas themselves are these weird off-diagonal things. But once we form the generators, these are the things that we feed into the exponential map to create the matrices that act on the spinors. They just have this nice block diagonal structure. So the upper left will act in the first SU2 in the same way that a sigma acts in a normal spin SU2, and the lower right will act in the second SU2. Okay? The only catch is that there's a relative minus sign between them. And if I crank out some of the other generators, I'm not going to show you the details, but if I do a spatial, so this is a rotation, then this comes down to 1/2 epsilon ijk sigma k, 0, 0, sigma k. Okay? Again, you get this nice block diagonal structure. And if you do a concrete example of this, like sigma 1, 2, you get 1/2 sigma 3, 0, 0. So the rotations work out very similarly. So a rotation in the xy plane is just given by the usual rotation around the z for the first SU2 and the usual rotation around the z in the second SU2. Here, though, you don't get that extra minus sign that you got for the boosts. It's okay. Boosts and rotations are different. What I'm writing down is you can completely and totally explicitly do this. This is just plug and chug. Okay, you've got the gammas. You can put them into this and bang out these matrices. Yeah,
So just to bring all the labels together, the sigmas with the single indices are the polyspin matrices. The sigmas with two indices are the members of the SO1-3 group. And gammas are the generators thing?
No, the sigmas with the two indices are the generators of the group.
And then gammas are the spinors? Or the
Yeah,
generators?
I know. The first time I did this, man, I was like, fucking kidding me, this is so hard. So psi is a spinor, and psi transforms according to this rule. I have a 4, sorry. I always get my factors of 2 and 4 confused. Okay? This is very analogous to what we did with vectors way back in the day, where we said a vector transforms to a new vector under the application of something, and I don't even remember my notation at this point, but it was like G, you could have written it as like G mu, theta mu, or something like that. This is horrible notation, actually. This is really god awful. Oh, here, let's cheat. Let's just do this. And then we'll do this. Okay, all right. So this is the vector, V. This is the transformation. This thing is entirely put together a rotation, but it's built from the generators G and the parameter sigma through this exponential map. Okay? The psis are a spinor. This whole thing is the thing you transform the spinor with. It's built out of the generators, sigma mu nu, and the set of parameters, omega mu nu. Okay? Where in all of this, you don't see the gammas. You're like, so where are the gammas? Well, the gammas you use to build the generators. Okay.
So with that set of parameters, omega mu, you listed it earlier as like a row vector that's 6 long, but it looks like it's a 2 by 2 type of thingy. Like it's a 0-2 tensor, kind of. Sort of, no?
It's a, no, so the problem with that, so the problem is you can't write it as a matrix because it has 2 indices, but they take 4 values. Remember, to write something as a matrix, you need the number of indices to be the same as the, or sorry, no, I'm crazy. I'm totally crazy. Forget what I just said. Oh, no. Yeah, you can organize it as a matrix. That's fine. Yeah.
How?
But the point is you don't evaluate it with matrix multiplication. That's the problem, is this full contraction of indices is not just matrix multiplication.
Sure.
It's actually matrix multiplication followed by a trace. But you could organize it as a matrix if you wanted to.
Okay.
So you might say, you've got 6 things. What frickin' matrix are you going to make out of that? Well, you're going to make an anti-symmetric matrix where the diagonals are 0,
okay.
and you have an off-diagonal set, and then minus.
It looks like the electromagnetic tensor.
Yes,
Okay.
exactly. Okay. Other questions? So it'll be an anti-symmetric 4x4 matrix. Okay. So what I'm going to try to do now, in the time we have left, is we've got a little bit about how things transform. Actually, I should point to this. We've got explicit expressions for the sigmas in terms of these gammas through this rule. Now what I want to do is that all-important step of saying, how do I make an invariant? Because our Lagrangian that we're going to eventually write down, it needs to be invariant under whatever transformations we're trying to argue are symmetries. So I know how things transform. So in principle, I can go back to that whole story we started the semester with, which is if I have a representation with a transformation, I just form the dual representation, and then I combine a dual with an original in the right way, and I get an invariant. Of course, as you might expect, there'll be a few subtleties. So let's see how this shakes out. And I'll leave that up there. That might work for me. Okay, so for SO3, which was equivalent to SU2 near the origin, we said that a dual spinor dagger psi is invariant for the dual being just equal to the original spinor. And this is equivalent to saying that the metric is the identity. Because normally we form the dual from the metric applied to the original thing, but I'm just saying it's the identity, so I got that. So let's see if that will work for these four-dimensional things. Oh, sorry, I guess in that story I was calling these chi's. So to distinguish it from what we're about to do, let me do that. Okay, so that's the SO3 case. So what we want to do now is the SU2 cross SU2 case. So we're going to try and argue or see if that combination is an invariant for psi twiddle being equal to psi. Okay? And to see if that's invariant, all we have to do is say, okay, this thing is really now just psi dagger psi, because I'm arguing that psi twiddle is just psi. So psi twiddle dagger is just psi dagger. And then if I want to transform this, this becomes psi prime dagger, psi prime. But I know how psi transforms. And so if I write this out, e to the I over 4 sigma mu nu omega mu nu psi dagger, e to the I over 4 sigma mu nu omega mu nu psi. Okay. I transform psi and then I take the dagger, and then this guy I just transform psi. Okay. Now, for the case of SO3, this all worked because of the following observation we made back then. We said, what I really want is for, well, first of all, if I'm Hermitian conjugating this, this is just psi dagger times the Hermitian conjugate of this. And for the case of SO3, we could say, these were real parameters. All of my Pauli matrices were Hermitian, so daggering didn't change these. So the only effect of daggering was to put a minus here. But then this with a minus here canceled this, and I was good. Okay? Is that going to work for us now?
You brought it up.
Yeah, I brought it up, and the sad truth is that it's not going to work. Okay? It's not going to work because, and if you actually look at the examples, I erased it on the board, but if you look in your notes at the form of sigma 0 I, and you Hermitian conjugate it, you'll notice that it's minus the original. However, if you look at the spatial ones, these are Hermitian. So it almost works. It works for the spatial ones, which again we might have anticipated at some level because we already knew that it worked for rotations. But it's the boosts that are screwing us up. And the boosts are just screwing us up by a minus sign. It's not that bad. It could be worse. Okay? All right. Okay. So, so we can fix it. And it turns out that the fix is actually pretty simple. So instead of defining my dual spinner to be psi, I am going to instead define my dual spinner to be I gamma 0 psi. Okay? So secretly I'm saying this is the metric I use to convert spinners to dual spinners. Okay? And so now we can run through how this actually looks. And so what we have now is psi twiddle dagger, I gamma 0 psi dagger psi. I'm literally just plugging in this expression for psi twiddle right there. Okay? This is equal to, I'm not even going to transform anything yet. I'm just going to massage this expression and then we'll transform it. So this is, well, at Hermitian conjugate, I reverse the order of things. So this is going to be minus I times psi Hermitian conjugate gamma 0 Hermitian conjugate psi. But what's the Hermitian conjugate of gamma 0?
Negative gamma 0.
It's negative gamma 0. Everybody see that explicitly? If you transpose it and change the sign in front of I, you just get minus what you started with. So I can erase the Hermitian conjugate there if I get rid of that minus sign. Okay? So now we can take this thing and we just transform everything in sight. And applying our transformation, we get something like that. It looks very similar to what we had before, except there's an I and more importantly a gamma 0. And then here's the really cool part. Actually, one more step. Let me distribute the Hermitian conjugation. Okay, so I'm just distributing this Hermitian conjugation that reverses the order. So I'm separately Hermitian conjugating these. And now here's the total and complete magic of this. That expression right there is equal to gamma 0 e to the minus I over 4 sigma mu nu omega mu nu. You know how I know that? Because you're going to prove it in your homework. So you will in your homework take exactly this expression and show that it's equal to this. But now you can see the magic because now this guy is just the same exponential with a minus sign. These two terms cancel. And what I have left at the end is I psi dagger gamma 0 psi. But that's what I started with before I did the transformation. Okay? So again, to find an invariant, you have to work with the actual transformations. Like, you know, what is it invariant under? Got to say what transformations I'm doing. So what we find is that some of the transformations cause a bit of a problem. Some don't. And to fix it, we have to use a slightly non-trivial dual. Okay, this is, if for no other reason, an inspired guess. There's no way you would have looked at it and said, I bet I gamma 0 would do it. It's not obvious. Okay? But hopefully I've convinced you that if you do it this way, then it seems to work out. Subject to you proving this result to yourself in the homework. Okay? You guys all right? Seem like you're hurting. Okay? All right, so I have one short page of notes to finish. So I don't think I'm going to be able to get through these today. But that's okay. That's okay. I think I've beaten on you enough today with the details. So, are there any questions about so I find that the big picture of this is really hard to absorb and get comfortable with. And a part of it is because what it requires of you is to generalize the framework in which you are used to thinking about these things. You get so used to thinking about doing a rotation by saying, I've got a vector and I hit it with a rotation matrix. And unfortunately, that thing which you're very comfortable with in no way, shape, or form provides you with enough generalization to get to spinors. They're just so detached from space-time. So what we had to do was reformulate the way you do rotations. You had to reformulate it in terms of generators and an exponential map, okay? And then you talked about algebras and so forth. And then with sufficient generalization, we could then take this big step of going from SO3 to SU2, and suddenly we could start doing everything for spinors, okay? No one in this world, period, is comfortable with spinors. If you leave this class, if you leave this semester, if you graduate and go and get a PhD in physics, you will still not be comfortable with spinors, okay? I think I told a select few of you at the end of the last class that Michael Atiyah, who was one of the best mathematicians in history, worked with spinors his entire life, and at the end of the day said, I still don't understand spinors. They're hard. They're really, really hard. But he actually likened it to the following. He said, spinors are he basically says, we understand the algebra of spinors. Like, we understand all the little steps here. I mean, they might be not familiar to you, but the steps are steps we've done in other places. But trying to wrap your head around, what does the square root of a geometry mean? He said that's a lot like when people historically struggled with what would the square root of -1 mean. But he said they eventually solved it and they're comfortable with it now. But it took a long time to get there. And spinors are not an old subject, right? Spinors they're the last 100 years at best. And we're still struggling with really trying to get a proper understanding of them. So it's not something that you should be down on yourself about if you're not comfortable with it, if you struggle with it. We all struggle with it. It's really, really hard and no one is completely comfortable with it. But I promise you, if you stick it out, as the course progresses, the way that we'll actually handle spinors is just going to become very sort of flowy and you won't really have to think too hard about the guts of it. I just can't hand you a picture and say, trust me, there's a lot of machinery underlying this. I feel like you need to see some of that machinery, especially if it can connect to things you've already seen before in other classes. Okay? All right, that's it for today. See you on Thursday. We will see you on Thursday. We're not going to cancel class for basketball game. Although it would be a lot of fun. Kelso has size 14 feet. Oh my God, it's ridiculous. It's insane. He is a